stream is about to start. We'll talk about code or whatever we'll talk about today. It's about to start, so please hang tight while I check that everything is okay. Sound check, camera check, lights check. How's my hair? Oh, wait, I don't have any hair. Maybe put some pants on and I am good to go. So get ready wherever you are, 'cause this stream is about to start. Get ready wherever you are, 'cause this stream is about to start. Hi, my name is Leandro Facchinetti, and let's write some code together, shall we? Very special day today. We have been working on this JSFX library that allows you to create real-time audio effects in REAPER. And we have been working on this library for the better part of this last year on these almost daily streams. We finally finished last week the first effect using the library. And of course, it took us this long because we explored many tangents, right? We didn't spend the whole time just working on the library. We investigated different ways of developing JSFX. We explored concepts like SVF filters. I really hate to say SVF filter because SVF stands for state variable filter. So I'm sort of saying state variable filter, but that's how people typically talk about them. Anyway, we explored concepts in digital signal processing, in the JSFX language itself. It took a while, but we finally had our first sort of showcase effect, because it's just showcasing a waveform display. It's a useful thing to have, but it's nothing to write home about. I hope that this next effect we are going to start working on today will be something more remarkable. So we will be using our library and revisit my first JSFX, the Automixer, and we will come up with version 2.0 of the Automixer. And along the way, we will fix bugs, we will add features, we'll streamline stuff, we'll develop a better user interface, and we will be using the library this whole time. So we will need to extend the library to add features necessary for the Automixer to work. Before we dive too deep into that, what's an Automixer? Why would you use one? What are we going for here? An Automixer is an audio effect that is mainly useful for a situation where you have multiple people in a room and each person has their own mic. So when they speak, the sound of their voice goes into their mic, but also bleeds into everyone else's microphones. And you want to get rid of that bleed because that is mostly echoes in the room or noise, or other people are fidgeting while the other person is speaking and you would like to lower the gain on their microphones. And all of this is automatic, which is essential because you may want to run an Automixer live. In fact, I have heard of people who run my original Automixer 1.0 in live settings, in some sort of roundtable event kind of thing. It's useful for podcasts as well, in post-processing, in editing and mixing a podcast. So it's useful in many ways to remove unwanted noise from microphones that are open in a room. And to begin with, we need to implement the basic functionality, which happens to be super straightforward. We will need one component that we currently don't have in the library, but there is a chance that we'll finish this, the core of the Automixer, in one session or two. It's not that complicated. And we'll dive into how exactly this works. Now, you could also perhaps use the Automixer for other purposes if you have multiple microphones in an instrument or on an ensemble and you would like to auto-mix stuff, but really it's not with the intent of auto-mixing, despite the name, not with the intent of auto-mixing music. It's more for spoken word situation. All right, before I dive into the technical stuff, hello Watchman Studios, hello Fotis. It's great to have you all here. Thanks for joining me. Very exciting day when I'm starting a new plugin, and it will be a relatively big one. It is my biggest plugin so far. I think that we will end up building bigger plugins, but this one is very special to me because it was what got me into JSFX in the first place. Okay, so let's start with the component that is missing in the library. Or better yet, let's start with the skeleton, the boilerplate, just to get this out of the way and have something on the screen. So let's go to our previous effect, the one that we finished last week. And in the future, I will document the library and I will have some sort of boilerplate that you copy and paste to start all your plugins. But while we are still in development mode, I will just take the previous effect and modify it to get the skeleton. So this will be the development version of the Automixer, and this name is necessary because I also have the Automixer installed from REAPER, the one that you can get going to my repository, and here it is. Oh, hang on, no, okay, that's right. So here it is, and I don't want confusion between the two. Hence this extension. Of course, I will have to remove it before I release it. Then there will be a bunch of sliders, but my sliders on the Automixer are completely different. This is part of the boilerplate. I do need to include the library. Now, this is a contentious point. I am thinking about putting it in the library in the first place. For the Automixer, I don't think it makes a huge difference to have this. I will not have it for now. If we feel like we need this, we will come back to it. What this does, by the way, is it prevents the init section from running anytime you hit play in REAPER. Then all of these things are specific to the other effect, so I can get rid of all that. Then the slider section, also specific to that one. This is part of the boilerplate, so is this. All of this can go, and I can keep these numbers for now. And all of this is specific to drawing waveforms, so I can get rid of all of that. So this is a good skeleton, and I think that I can load this in REAPER without syntax errors or anything. I started typing waveform, got used to it. And here is our Automixer, and yes, it is just a black screen, no sliders, no nothing, but it loads, so no syntax errors. So there are two things I could do now. The first is computing RMS. We don't have that in this version of the library. The second is inter-plugin communication, because my Automixer 1.0 uses this relatively complicated REAPER routing situation that doesn't translate to other DAWs, which is not the biggest deal because JSFX are not even available in most other DAWs unless you use some compatibility layer, and I have never tested the Automixer on these compatibility layers. I don't really care. But I am tempted to change the routing of my Automixer in an incompatible way with the previous version, by the way. It will require a new setup. But I am planning on doing this in a way that will work in other DAWs in C++, because I am also developing an Automixer in C++ as a VST audio unit and so forth. More about this tomorrow on the C++ Digital Signal Processing Juice study group. But I think I would like both versions to sort of be set up the same way. So perhaps you would install the Automixer in Reaper, you got used to it, you would like to work in another DAW, you can just take the VST version and continue working in exactly the same way, same settings, same concept of routing. So we would need to do something that I showed in another meeting of the C++ study group, and that is to have a bunch of plugin instances sending audio and one plugin instance receiving audio. I could handle this right now. So I can either go with RMS or this extra routing situation. And Tail is here. Hello, Tail. I think it is more interesting to do RMS. And there is a previous version of the library that we implemented around January or February that has RMS computation, but as far as I remember, that version didn't deal with the case of multiple channels. So let's just re-implement the thing from scratch because the library changed so much anyway, the data structures and everything, that I might as well just re-implement RMS. It's a simple algorithm. And despite being simple, there is something you have to know when computing RMS when it comes to multiple channels. So we'll get into that, and it will be interesting. I don't know exactly where I want to put this. Perhaps near the circular buffer, because it is implemented with a circular buffer. It's kind of a circular buffer. Yeah, I think I'll put it here. And I will spell out root mean square. That's what RMS stands for. And it's also a description of how to compute RMS, which is very convenient. So the idea of RMS is you take a bunch of samples. We will have a window of samples that we can adjust. Then take the squares of all the samples, take the mean of those squares, and take the square root of that mean. So this is just spelling out what you need to do, right? And you could just take the window and do exactly that, square, mean, and root. But that's relatively slow. So there is a very old video in my channel, it's about 2 years old at this point, in which I explored 3 different ways of computing RMS, and I landed on one that is fast, precise, easy to implement. And that's what the version we are implementing. But we can go, if you're interested in knowing more about this, go watch my videos about 2 years ago about RMS. So we will need a data structure that holds the current sum of squares, right? The sum of squares is necessary to compute the mean. The mean is the sum of the values divided by the number of values. So we will need the running sum. We will need a circular buffer of squares. And that's about it, actually. So let's have a data structure with 2 fields. I will have and typically I don't like to abbreviate things, but RMS is almost more popular than root mean square. So I think I will keep RMS in the name. So I will have the running sum of squares. See how I like descriptive names? That will be position 0 in my data structure. I'll also have, oh, it's squares plural. I will also have the squares, and that will be in position 1 of my data structure. And finally, I will have, hang on, what else do I need? I probably also need the size of the window. Well, that will be embedded here, so I don't need to store that separately. I think that that's all I need, right? The running sum of squares and the squares themselves. So how do I create a new one of these data structures? You need to give me the length of the window. Well, if we want to be able to adjust the size of the window, then this length needs to be the maximum length of the window, but you could set smaller windows. Setting smaller windows is not exactly trivial. Or actually being able to change the window size is not exactly trivial, but we'll get to that. First, let's just consider the case where you have a fixed window that doesn't change. It's not a slider. The window's length is not a slider. So I will create a local variable called RMS. And it will be a chunk of memory with 2 slots. And I will return RMS at the end. And then I need to initialize these things. The running sum of squares starts with a 0 because that's the identity of the sum operation. The identity? No. Well, it is. But more importantly, it is the 0 of that operation. In that, of the group plus, algebra is complicated. And then this needs to be a circular buffer of this length. To create a circular buffer, that's all I need to provide. Am I right? I am. So this creates a new one of these data structures. Now, let's have 2 functions. Oh, so I guess I need a third field in the data structure. One of the functions is add a sample into the current RMS, or the current square. And the second function is advance the pointer of this circular buffer. Do I have this kind of control on the circular buffer? I went back and forth with this and I don't think I have it right now. Yeah, I don't have a way of setting values. I only have a way of pushing values, which advances the pointer. That's all right. Okay, so I guess it can be field 0, actually. I have the current square I'm working on. I'm gonna call this a square in progress. The running sum of squares and the squares. And now my data structure has actually 3 fields. The square in progress also starts with 0. For the same reason, actually. It is the 0 of the plus operation. All right, so I will perhaps call this add into the RMS a sample, or maybe even a value, because you may be computing RMS of something that is not a sample. Maybe you're computing the RMS of an envelope because you're doing a limiter. I don't know. So what fields am I going to need? Well, I will only need these 2 fields, I think. And I think that at the end, I will probably update these 2 fields. So just go ahead and do it like this. Actually, I won't need the second one. It can go. Okay, so I will need to square a value and put it in the squaring progress. So I will square in progress plus equals square of value. And this is the trick that I explained in my video 2 years ago. but it's the subtle point you need to get right if you want to compute the RMS of multiple channels. The trick is, first of all, you want to combine the multiple channels after taking the square, not before. And the reason for that is, suppose you have two channels that are exactly nulling. So one is exactly the opposite of the other. The signals cancel out. Now, if you do the combination before taking the square root, they are going to cancel out and you're going to end up with a bunch of zeros. But that's not the RMS is a measure of like energy. It's a measure of how much energy a signal has. And signals that cancel out don't have zero energy. If you have different signals that are canceling out on your left and right speakers, you are going to hear sound. It may be perhaps lowering volume, but it will be there. So as a measurement of energy, you want to take the square root first, and then all the values will be positive. Then you add them up. And I think I will need another variable here to store the number of channels. And also I will need the length of the window, but that's stored here. But these are not stored there. Yeah, so let's have another field. And this is like channels length, something like that. And now our data structure has 4 fields, and we need to initialize this. And I think I will just ask the user for this. So perhaps I will call this the window length. And I'll call this the channel's length. Yeah, okay. That will do for now. So the window length is what is the period that you're taking the RMS of? How many samples are this RMS about? And each moment in time may have multiple channels. This information I'm just storing, I'm asking the user of the library to provide this to me. I'm storing this for later because when we get to actually take the root, we will, or actually when we take the mean, we will have to have this information. Okay, so let's have another function called, oh, hang on, I forgot about declaring local variables here. All right. And this will be like advance. Yeah. And to advance, I will need this field. This one. I will also need this field. So I'll take this circular buffer and I will push the square in progress in there because the square in progress is actually finished, and I will reset it. Also, I will need to update the running sum of squares. So let's get... Oh, come on. I used one variable instead of the other. I am all messed up here. Let's fix this. Okay, so there is the list of squares, and I will take the square in progress and push into that. Also, the running sum of squares. I will add the square in progress, and I will subtract is it called get? Yes. And I will also need the length of the window, which I am just storing on the squares. So let's have another local variable, squares length. So I am updating the running sum of squares. We have already squared the values, so the S part of RMS is done. Now, we are just storing the sum of a bunch of squares. The mean and the root will be taken later. I'm just storing the running sum. To update the running sum, I need to add the current square in progress. That much is probably straightforward, but what may not be straightforward is that I need to kick out of the running sum of squares the sample or the value or the square that got too old, that is falling out on the other end of the window. And this is what this is doing. So and that's actually the reason why we have a circular buffer for the squares, is so that we can do this subtraction. So we can kick out of the running sum of squares this old value. And it is important that we do these two operations in this order, because we always want to read before we write. And I think that this does it. So for the next function, we'll actually get. And you may note that there are 3 field access here. This is just accessing a field from the squares, but these are 3 field accesses from the RMS data structure, and there are only 2 writes. And that's because the squares are the base address of the circular buffer. It doesn't change. What changes is the values of the circular buffer, and that is already taken care of. So now, to get the RMS, we have been collecting values into the RMS data structure. To get something out, we are going to need these 3 fields, I think. And we are not changing anything, so we will not need to write anything into the RMS data structure. Now is the situation where we have a running sum of squares, so we just need to divide by the number of squares to get the mean. So I guess I will need a line like this. Like so. Right, so RMS, we have already taken care of the squares. Now let's take care of the mean. You take the running sum and divide by the number of squares, that's your mean. Then to take the root, you take the square root. Square root. And that's RMS. Hey Bo, I'm doing well. I hope you're doing well too. I'm very excited. We're restarting Automixer 2.0. This is a great day. I think that this is the kind of thing that can be tested. I think that this is the kind of thing that should be tested. Let's test this thing before we start using it in the Automixer. I will first create some RMS computation. The length of the window needs to be something relatively small for me to be able to plug values in and make sense of things. So I'll have 3 samples and 2 channels. Then when adding a value, I think it can be cute if I return the square in progress. Oh, that's what I already do. Okay. Then to advance, what does push return? It probably returns this. Doesn't matter a whole lot, but I think I will return this. No. This is the kind of function that you shouldn't be relying on what it returns. But get is the kind of function that you should be relying on what it returns. So I think to set up this test, I will create this data structure as I did. Then I will add a bunch of values, advance the pointer, and try to get some stuff out. Yeah, okay. Oh, I am missing one part, and that's crucial. When taking the mean, I need to be dividing not only by the length of the squares, but crucially, divide by the number of channels as well. And to divide by both, I can just multiply them on the denominator. This is crucial because we have been accumulating multiple samples per square, and we need to take this in account. All right. I guess we can just plug some random values in here. So now there are 2 samples. Yeah, okay. So there are 2 samples on this one slot. And then I advance. The rest of the slots are supposed to be 0, so we should be able to test just this for now. If I try to get the RMS, it should be equal to the square of 2 plus the square of 3, all of that divided by 2, and all of that square root. Very simple test. Let's hope that this passes. Hey, it fails. Well, let's take the advice here and open the editor and check for variables that shouldn't be global, because sometimes that's easy to fix. And nope, just the version. So let's dive deeper. Let's go into the library. Look for RMS. And run this interactively. So when I run this, I get some random number here. It's not a random number, but we get some arbitrary number here that is just the location of the RMS data structure in memory. And we get the square of 2, and here we'll get 9. Oh, hang on, 13. Oh, it is 4 plus 9. 4 plus 9. Then we advance. And then it would be nice for us to check what is the running sum, which should be 13. 4 plus 9. And perhaps there is a mistake in here. But before I start writing some debug code, I do want to commit what I have, because at least it is syntactically correct. So what is the RMS running sum of squares? It should be 14. Or 13. It should be 13, because it is 9 plus 4. And it is 13. So the running sum of squares is correct. And if we get the RMS, what number do we have? We have 1.47. And if we look at this, what is it? Oh, okay. Oh, there you go. It is the same mistake I made here. I also made here on the test. I'm dividing by 2, which is the number of channels, but I should be dividing by 3 times 2. 3 samples, 2 channels. And now this should be 1.47. And it is. So now the test should pass. But not this file. That one. And it passes. Great. Can we write better tests for this? Most probably. But I'm eager to continue, so I will continue. Oh, and I already know of 2 things that I want to do to RMS. To do. Allow, I'll put the to do here. Allow for changing the window size or length. I'm calling this the window length. Allow for changing the window length will be an essential feature of this. But let's try to do the Automixer algorithm with this implementation of RMS, which is more or less working. Okay, on the init block, I will want to create one of these data structures per Well, it is complicated. I want to create one of these data structures per track or just one of these data structures in general. I think I want to create just one of these data structures in general. I think so, but I'm not 100% confident. We'll see. We'll start there. The length of the window can be 300 milliseconds, and this number is actually given in samples, so I will need my very useful milliseconds to samples converter. And the length of the channels will be 1. I will have only one. For now, I'll have only one channel on this RMS computation. Yeah, let's start simple. Let's start there. Then on the sample block, I am just adding and advancing. Super simple stuff. But I can, just to see the result of this, set the RMS as my output. And then we'll be able to see if the RMS, it's even a better test than the unit test we wrote. It's just not as easy to run and reproduce. That's the value of having a unit test, but this will be an actual test of our RMS computation. And as I run audio through this, we can see that the right channel is unaffected, and it's bouncing up and down along with my voice. But the right channel is slightly lower in volume, which is good indication because the peak is always bigger or the same as, but usually it's bigger than the RMS. And this is moving more slowly. So I am going to say that this looks like an RMS. It quacks like RMS. It's probably RMS. I have 2 instances now. Okay, so this is the RMS in terms of amplitude. We'll need this in terms of dB. Well, not quite. There is a workaround for this. We'll get to that in a moment. I'm scoring a short film and listening. Okay. Don't you have to recalculate the sum now and then to prevent floating point rounding errors from accumulating? Maybe not, because JSFX uses doubles. Okay, I didn't get into this, but let's get into this. So what Toyota is talking about is super interesting. It is about this. The interesting thing about this is that these are not numbers as in mathematics. They are numbers as in computer science. You would guess that they are the same thing, but they're not. In computer science, we use these so-called floating point numbers. And it could be that you start with a number x, you add y, you subtract y, and you don't end up where you started. It's not the same as x. Because of rounding errors, because of implementations that try to optimize for fast arithmetic, because of reasons, this doesn't always hold. So I am adding stuff into the running sum, and later I am hoping to subtract stuff from the running sum and get back to where I started. But because these are computer science numbers, they're floating point numbers, this doesn't always hold, and these little mistakes, because it will be off, but it will not be off by much. You will not get to x, but you will get very close to x. So there is a small mistake, but the problem is that these mistakes accumulate over time. And you could end up way off from where you started. And that's a theoretical problem that I have not run into in practice. I have been calculating square roots, RMSs like this in my Automixer for the longest time. I have seen other plugins that do this as well. I think that including some plugins by Caucus. Not that they are like the ultimate authority in writing plugins, but it is where I learn some of my JSFX. And it doesn't seem to be an issue. Maybe, as Tail guessed, maybe it is because all these numbers are not mathematical numbers, they're computer science numbers, but they're doubles. They are not just simply 32-bit floating points, they are 64-bit floating points. Every number in JSFX is a 64-bit floating point. So we have a lot more precision. And perhaps this precision is what is fixing the problem here, because it is so, the error here, it can occur. You could end up with a different x from the x you started with, but the error is so small that it doesn't matter. Maybe it has to do with the protection over non-normals, the normalized numbers. They tend to be very small numbers, or they don't tend to be, they are very small numbers, so maybe the protection for denormalized numbers is kicking in here somehow and fixing things. I don't know. I just know that in practice, I haven't run into the issue. If I ever run into the issue, then Tail is correct, and the one possible solution is to just keep a counter. For how long have I been using this running sum of squares? Oh, it has been a while, hasn't it? Maybe 1,000 samples, maybe 1,000 years, but it has been a while, hasn't it? Okay, so I'll just ditch this and recompute the running sum of squares just by looking at the squares array, or circular buffer, I should say. Just by looking at the square circular buffer, I can always recompute this, right? Because this is here just for performance. I keep this running sum of squares just to make things fast. But in theory, I could just always compute everything based on the circular buffer of squares. So that could be a solution. And there are people online who will tell you that this is strictly necessary and that they do it. Perhaps they are doing floating point arithmetic. I don't know. You're most likely to run this when sending many zeros after a non-zero value. True, and this is actually something that occurs in the Automixer. If you are just using the Automixer live, or if you are using the Automixer on tracks that you didn't edit in any way, this will not happen. But there are people who will use something like dynamic split to carve out all moments of silence, or perhaps they're using a gate before the Automixer. So whatever the case may be, they will be sending bursts of speech followed by gaps of many zeros. So I agree that this would be the best way to trigger some issue. It never occurred in my experience. So I will continue doing this until it falls apart. That's what I will do. Did you ever run into this, by the way? Since you are bringing this up, did you run into this in an actual plugin, or like me, you read about it online and you were like, I don't know, could be one way or the other? I'm interested in knowing. And thanks for catching, because this is a subtle thing. I was sort of avoiding the conversation because it is a subtle thing. Okay, so let's try to finish this algorithm. It is not that complicated. Hopefully we'll be able to do it. So right now we are doing all the computation on one channel. But let's do the computation on 2 channels. And then I will add the left and right channels, and then I will advance the pointer. So now we are taking the RMS of left and right. Really, what I'm going for here is the RMS of all the different microphones in the room. I'm just approximating that with just stereo, so pretend that there are only 2 microphones in the room, because I want to make things as simple as I can. Okay, so I will say that RMS current is equal to RMS gauge, just like that. And then now let's compute the dB of all these values. Now, as I said before, I'm going to do this in dB. You could do this linear. You could do this with samples directly and RMS directly. I would do it, and in fact, I did it with samples directly. So if you go look at the original implementation of my Automixer, and I have a code review of this in my channel, just browse in my video history. And I did this linearly, which is better because it is faster than to convert to dB and then back. But I'm going to do it in dB because I will need these values to do visualization, because the original definition of an Automixer is using dB. If you go look up online about an Automixer and how it works, people will tell you stuff in dB. So I'll do everything in dB. And I think we'll need dB for visualization anyway, so I might as well just compute it. And we have a linear to dB. We do. There you go. Now we have the RMS and the samples in dB. Okay, so let's talk about how the Automixer is going to mix the microphones. It is going to say the microphone that has the highest noise or signal, I should say signal, not noise. The microphone that has the loudest signal will have very little to no attenuation. The microphones that have less signal will be attenuated more. It's never the case that we are gauging, so there is no notion of threshold in this algorithm. And there is no notion of adding gain to anything. We are always attenuating. And we are attenuating in such a way that the sum of the levels allocated for all the different microphones will add up to 1. In other words, it is as if instead of having multiple microphones in a round table, you had one microphone and people were just passing it around. Oh, that actually makes me think that I am not computing stuff that I need to compute. So I'll get to that in a moment. No, but I do see my sum hanging at blah, 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 or something, when it should go to 0. Fair. I don't think I saw this myself, but I believe, of course, that this could happen in my implementation, because I'm not preventing against it. But I also think that this is okay. If I have a very small value, it will probably mean that if some people are talking and then all of a sudden all microphones shut up, all microphones don't send like low level noise, they just literally stop sending signal. Maybe you edited out some part of the conversation or you put a gate before the Automixer, so you have a bunch of zeros in a row, then this could end up in my running sum. And I am okay with this. I don't think it matters too much. Perhaps in that case, what would happen is my Automixer would get stuck allocating a lot of gain to one of the microphones, but they're all silent, so it doesn't affect the end result. Right, so what I think I need is 2 RMSs. I have an RMS of 2 channels, but what I should have instead is 2 RMSs. Kind of misremembering the algorithm before. Let's do this again. We'll have just 1 channel per microphone, but we'll have 2 microphones. And I will give them imaginative names of 0 and 1. Then we will advance and get the dB. Of both channels just like this. How do I hate having to copy and paste code like this? I feel dirty. But we are just doing something quick and dirty, so that's okay. So now I have the computation of one of the microphones here, and another one of the microphones there. And then I have the current RMSs of both microphones. Okay, I'm in good shape again. And I will paste this up here because it only deals with samples. So it doesn't depend on RMS, so it belongs in the beginning of the sample block, I think. So now let's add all of these. And this is like the total gain that I'm allowed to allocate. Then for the left channel, the gain of the left channel is this minus that. Did I get this right? I don't think I did. Should be the other way around, shouldn't it? Total gain yeah, let me stare at this for 5 years and I'll tell you if I got this right. And this is even in dB, which I should also convert back. Let me finish writing what I have in my head and then we will review to see if it makes sense. Okay, so let's begin with this part because it is relatively straightforward. This is me applying the gain. I said that we will have gains for all the different microphones. We only ever attenuate. So maybe I should, instead of calling this gain, I should call this attenuation. There you go. We never add gain. We only ever attenuate. So this is me doing the attenuation. I just take the samples and I multiply by this attenuation that has been computed. Simple stuff. To apply the attenuation, just multiply. Now we need to get into these 3 lines, and they are the bulk of the algorithm, which I'll probably get wrong a couple times. I will probably get it wrong a couple times because I am thinking in terms of linear, but I want to do this in dB. If it doesn't pan out, I will do this in linear. But let's think about how this goes. Let's say that person 0 is speaking. Okay, so person 1 is speaking. We should be allocating more gain to this person and less gain to that one. We should be attenuating this person more, and we should be attenuating this person less. So I have the RMSs, and I add them up. In dB, let's say that the RMS of this person who is loud is -12, and let's say that the person who is quiet is at minus, let's say, 50 dB. Because there is always some bleed into the other microphone, -50 seems like a reasonable value. So what is the total attenuation in dB? I'm adding both of these numbers. So I end up with -62. I did this in my head, I'm so proud. Then let's see what the attenuations will be. It is -62 minus -12 minus -50. And as we all know, these 2 minuses are going to become plus. So we end up with -62 minus -12 minus 50. And that's a coincidence. Let's pick different values then. Let's pick 40. And then the addition is 52. It is not a coincidence. It's not a coincidence. Yeesh. I don't know. And this is going to be -12. Interesting. Let's see. These are the attenuations in dB that I'm going to apply. So I'm going to convert them back into linear before I multiply. What am I going to get? Maybe this is the most roundabout way of computing dB into linear, but it is the first thing that came to mind. Okay, I am multiplying by a very small number. That seems wrong to me. 003. And how about -12? That will be a larger number. And what's worse, they don't add up to 1. So my logic really is flawed here. Perhaps I am having a hard time because I want to do this in DB, and I will do this in DB at some point. But perhaps to begin with, I should not do it in DB, because then I can get my head around it, because I did this already a couple times before. Or maybe Tail is going to tell me what I'm doing wrong. Oh, you have to deliver it in 2 hours and 40 minutes. Good luck, Fotis. Okay, and this is not going anywhere. I am not able to think in terms of DB for this problem, which is funny because the original definition of the Automixer is in DB. But the trick is we are adding and subtracting stuff in DB. And when you do that, it is equivalent to multiplying or dividing in linear because of logarithm laws. And there is a logarithm in the computation of linear to DB and vice versa. So the way that I think about it is in terms of multiplications and divisions, which is supposedly faster because you're not converting to DB and then back in the first place. So when the original implementer of the Automixer, I think his name is Corey, implemented the first Automixer that is available in Repack, comes with the default repositories even in Repack. When he was implementing that, he realized that, oh, I don't need to convert to DB, add, subtract, convert back to linear. I can just do all the operations in linear by multiplying and dividing. And that's what he did, and that's stuck in my brain, and that's how I can reason about this. Before I give up on the DB stuff, let's just briefly invert these two values to see if it makes more sense. Okay, what are we going to get out of these? Minus 12 minus 62 is 50. So I just bet that I will have the same numbers, but they will be positive. This is not going to go where, because it's going to be above 1, is it not? Yeah, it's way above 1. So yeah, this is not going to fly. Second try. I will not do anything in DB. I will do the computation of RMS. I'll skip the DB stuff. Something like this. Okay, total. What is it? The total. What am I looking for? I'm looking for a sum of RMSs. So this is like level. I'm gonna call it level or total signal. Yeah, that's what I'll do. So I can just add these two guys. And that's the amount of signal that I have available to me. So that's the signal coming out of all microphones combined. If multiple people are speaking, then this will be a bigger number. If there's just one person speaking, this will be a lower number. And if no one speaking, this will be close to 0. Then I take these two and divide by the total signal. Now you may be wondering, well, hang on, total signal may be 0, you just told me. If all the microphones are silent, this is going to be close to 0. And you're dividing by that. That's not going to fly. True. So here's what I can do. I can add an infinitesimal. Now keep in mind that these are positive values, okay? RMSs are positive values, or I should say non-negative, okay? They're non-negative. They're never negative. So if I add an infinitesimal, we are guaranteed to have a non-zero here. So this division will be valid. Now the question that is in everyone's minds is, did I spell infinitesimal right? And I did. Take that, internet. I spelled it right the first time. Okay, and this is how to do stuff in linear, and to me, at least, it's more straightforward, because what I'm doing is just taking the contributions. So if this guy is contributing 3/4 and this guy is contributing 1/4, then this is supposed to be 3/4, 1/4. And they're supposed to add up to 1 because the denominator is just the sum of the numerators. So they're supposed to add up to 1, and then just apply the attenuations, and that's that. Let's see if it works. And we are doing a mixing of left and right channels. Oops, this is the old Automixer. We're mixing the left and right channels, so I feel like I should send different signals to the left and right channels. Oh, but there is something even more surprising to me, and that's it is attenuating the gain here. It is attenuating the signal here. So that's odd. Let's look at the attenuation is half and half. Oh, okay, that makes sense. That makes sense, actually. The gains will add up to 1. So now both channels will add up to one of these channels. Okay, never mind that. I will do some funny routing here to test this. I will have my microphone here, only on the left, sending, not sending to, it doesn't matter if it sends to master or not. And I will have another signal here that will not be my microphone. It will be simply a tone generator. This will be only on the right. Both of these will be feeding my Automixer. So now we have signals on the left and on the right of my Automixer, and my Automixer is supposed to mix these two signals. And we can see that it's sort of working. When I speak, my gain goes up, and this other gain of the sine wave goes down by a little. Let's look at the attenuations that we are getting. Well, my microphone is too low with respect to the sine wave, so it never wins. But these numbers seem to add up to 1, which is the correct thing to do. So overall, the gain will be 1, which means there will be one microphone going around. And I can also lower the level of the tone and put it in a level that is closer to my microphone. So I guess -25 or something. And now my microphone and the sine wave are sort of competing. And if I stop the sine wave, my microphone gets louder. And if I return, so this is like two people speaking at once, then my microphone is lowered in volume, and so is the sine wave correspondingly. So there you have it. That's the algorithm for the Automixer. It's not complicated. Even if I made a bunch of mistakes here and I implemented the RMS from scratch, we were still able to do it in 1 hour, 15 minutes. I find this algorithm surprisingly straightforward and yet very useful. It sounds very nice. There is just the devil is in the details. There will be 1,000 small details that we have to take care of. But not today. Today we will read the rest of the chat and we'll say goodbye. So in dB, they should add up to 0 dB, right? When we say add, we mean in linear, not dB. Yeah, well, I have the hardest time reasoning about this. I know that this division will turn into subtraction in dB, but I don't really remember what to do with this part, and I guess that's where things fell apart in my attempt. And what you're saying is that the attenuations should add up to 0 dB, because 0 dB is 1 linear. You would be right. Yes, I want my attenuations to be all negative dBs because I want them to be attenuations, not adding any gain. And I want them to add up to 0 dB. But then the problem is, how am I going to add a bunch of negative numbers and get to 0? I'll have to reread the material on Automixers to remember this dB algorithm. Or maybe I will just go with this linear algorithm and whatever, you know. Yeah, I'll see. So here is the thing. Tomorrow we have a meeting of the study group. I am looking forward to that because I didn't do the stuff I promised I would, but I did something else that is very interesting instead. I'll keep you all in the suspense, but tomorrow on the meeting of the study group, there will be some circuits, actual components. We have been talking about analog modeling in the channel lately. I will be showing you small circuits that I built on a breadboard. It will be a lot of fun. Then on Thursday, we'll get back to this, and I think I will do the thing that I said I could do instead of RMS, and that is the side channels to communicate audio through, so that the setup for JSFX will be the same as the setup for my C++ plugin. That's what's up. So I see you tomorrow. Thank you, Bo and Tail and Fotis and the Watchman Studios and everyone else who's watching this. And thanks for supporting me on PayPal, Patreon, subscribing to the channel, hitting like, all these things that you do that help me. See you tomorrow. Have a good one. Bye. Thank you for watching the stream. You know how great it has been. Or maybe it sucked, and I am glad that you stuck with me. And soon we'll all be back together for some more coding or talking or chilling. The next time I'll be streaming.